Okay, I hope you guys are ready because today we are going to get into it a little bit. This might take a little bit longer than normal, but this topic is extremely important. Okay, so let's say that we start out with aliens. Okay, so one day some aliens fly down. This. Real long necks, kind of strange. These big eyes. Little tiny mouth. Little dangly arms. Wow. I got a whole bunch of legs. Sorry about the sound effects. Okay, so these aliens fly down to our planet, right? Now, what color are they? Let me think here. Nylan, what color should they be? Good choice, light blue. Okay, so while I'm coloring this, I'm going to explain it a little bit. We wanted to know if aliens are taller than humans on average. So that's what we're going to check out. Now, we are going to do a set of hypotheses to see what we can find out. So we've got our nice blue alien here. Nice. Looking alien. Let me do a little shading under the eyes here to make it pop a little bit. Okay, a little shading over the eyes to make it look like he's looking at us. A little shading under his gullet here. Actually, I don't know what a gullet is. Okay, so we've got our blue alien here. Now, what we did was we went out, and let me draw myself on here. So we have the typical average height male, which is Mr. Vasey. Right now, it kind of looks to me like these guys are a little bit taller than the average human. I'm just kidding, I'm super short. So this might not mean anything. But what we did was we went out and we measured the height of, let's say we got one sample. So one sample with, let's go with 20 humans and 15 aliens. Okay? Now, when we did this, we found that the average height of, and remember this is a sample, so we're using X bar, the average height of aliens, let's go X bar with a little a down here, equals, let's say, was 73 inches. Now, let's say that the average height of humans was, let's say, 67 inches. So obviously to me, after our one sample, it seems like aliens are taller than humans on average. But remember, this is only one sample. So this is where hypothesis testing comes into play. So let's do a hypothesis test. Now, we've got two hypotheses. The one is called the nutter butter? The null. Thank you so much for that. I appreciate the help. Thank you, BR. All right, so the null looks like this. Now remember, the null is always the boring hypothesis that states nothing's out of the ordinary. So the null would say something like this. It would say that the average height, X bar, right? Wait, somebody stop me. It shouldn't be X bar. Why not? Take a second and think about it. Why should the null not say X bar? Because our sample had X bar in it. I'm trying to think. Why not? Tony, you would call me out on that. Remember, our hypotheses always have the population parameter, the symbol for population, because we're guessing or hypothesizing about the population. So I'm not going to use this. I'm going to use the null is going to say something like this. If I had to take a guess about the whole population, the null is always going to say, hey, the average height of aliens is equal to the average height. And remember, this symbol is mu, or it's the average of a whole population of humans. The null says nothing's out of the ordinary, right? They're the same. There's no difference. Now, you might have had a sample that was a little bit crazy, but on average, they're right around each other. Okay, so that is the null. Now, our claim, known as the alternative hypothesis, which looks like this, is going to say that the average height of aliens is greater than the average height of humans. Because remember, we're making a claim based on the information that we have. And the information that we have is our one sample, where these blue aliens in our one sample were on average quite a decent chunk taller than the average height of our humans. So now, once you have these hypotheses set up, you're gonna want more than one sample. Now, this is kind of like what they do when they're trying to test the waters to figure out voter outcome, right? So when a big election's coming up, they go out and they get a bunch of samples. They take a sample of 500 here, a sample of 1,000 over here. And that would be nice if we could get multiple samples, right? If we could go out and sample alien population and human population here, go out and get another sample here, go out and get another sample here. We ain't got time for that. So the deal is, we're going to use some computer simulation. This is where computers are very, very handy because they can do something called sampling distribution. What a sampling distribution is basically just a bunch of samples. So, for example, if we have a plot like this, and let's say that our sample outcome, for whatever, if we're doing our alien population or something else, but our sample comes right here. Well, that's nice. We've got one dot, but we want a bunch of dots. We want a bunch of samples. A sampling distribution is like magic. It's like if you have a $5 bill, you stick it in the magic computer and it's like bzz, 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 spits out a whole bunch of $5. Actually, that's called counterfeiting. So that's illegal, so don't do that. But it's cool because it's like you have one sample, you put it in the computer, and the computer can manufacture a whole bunch of other samples. So it's going to kind of turn out like this. And then you're like, okay, now I've got a lot of data to go on. That's what we want, a sampling distribution. So in a sampling distribution, hint, 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 triple hint, J-Lise, this one dot in a sampling distribution represents a whole sample. It doesn't represent one person. It doesn't represent one item. It represents a whole sample. Now, when you get a sampling distribution, this is really nice because you can tell how rare your sample was or how extreme it was. And we're going to talk about a very special letter that tells you how extreme your sample was. So the special value that we're going to use is called a p-value. A p-value will give you a decimal that will tell you one very specific thing. Now let's say that we're looking at this distribution right here. This dot does not look very rare. It's right in the middle, clumped up with all the other data, right? It's not out on its own. So a p-value, let's say, might equal something like, and this is just totally a crazy guess, but let's say 0.53. Now, A p-value stands for this. It's going to tell you basically the proportion of samples that are as extreme or more extreme than yours, given that the null is true. So basically this is telling us we've got about a 50% chance to get a sample as extreme as ours, because 0.53 is 53%. Now, that's not rare at all. That's like flipping a coin. If I said flip a coin and you got heads and I was like, oh, no, you didn't. I mean, we'd all know, well, you had a 50% chance. That's not rare. That's not extreme. If the p-value is extreme, it's going to be low or close to 0. So, for example, let's say we get a p-value that is equal to 0.02. Well, what does that tell us? That tells us that we had a 2% chance of getting a value that extreme, given that the null was true. So if the null was true, we only had a 2% chance of that happening. Now, is that rare? Yeah. If I said you had a 2% chance of passing and you passed, you would be like, whoa, that's amazing, because we all know that's a pretty low chance. Now, of course, there is a very special value that is the cutoff that we use to tell you if a p-value is low enough or not. I know this is getting a little confusing. You might have to watch this video 7 to 12 times, but the cutoff value is known as alpha. Alpha, for our intents and purposes, is going to be typically 5%. If the p-value is lower than 5%, so think about it like this, 5% or 5 cents, a nickel. If it's not silver, if it's lower than a nickel, then that is pretty low, right? So if the p-value is less than 0.05, then it is extreme or it is low. This is what you do if the p-value is low. Let me show you. Let's say that we had this p-value right here of a 0.02. Now, 0.02 is less than a nickel. It's less than 5%. So this is the rule that we follow. If the p is low, the null, and I would remember this. In fact, I'm going to probably sing it to you. The null must go. So here it is.
If the p is low,
the null must go. If the p is low, the null must go. So basically, the null is trying to tell you that everything is normal. Your claim is saying, no, I don't think it is. Well, if you do a sampling distribution and find a p-value that is lower than 0.05, then you can reject the null and you can accept your claim. So originally, I said that aliens were taller than humans on average. The null said, no, they're about the same. Let's say that I came out with a p-value, forgot my L, of 0.03. Is that less than 0.05? It is. So the p is low, the null must go. So that tells me I reject the fact that they're the same height. I accept my claim that aliens are taller than humans on average. I hope that makes a little bit of sense. I'm going to give you some nice practice on this coming up the end of this week. It'll be due on Sunday, and I'll put it up there probably tomorrow. It's not going to be hard, but it will only not be hard if you watch this video at least once. I would recommend watching it twice. I know that's a lot to ask, but I want you to get it ingrained in your system and then answer these questions, okay? All right, love you guys. Peace.